Hello, welcome to the oral session of Seismoacoustic Sources in Theory and Practice. I am Paulina Bittner, and my colleague Paulina Feitio is here to take the questions from the audience. We are very happy that you joined this session and are watching it. We have three presentations from Yochai Ben-Horin from Israel, from Sarah Albert in the US. Welcome, Sarah. It must be very early at your place. And from Ryan Modrak. All presentations will be played, were pre-recorded. However, Yochai and Sarah, and we hope also Ryan, will be there to answer your questions. So please don't be shy. Paulina will definitely be watching out for your questions, and we will like to ask them to our presenters. The first presentation is from Yochai. It will be on observation of surface explosions in Israel, and it is a pre-recorded presentation.
Shalom, I'm Yochai Ben-Horin from the Israeli NDC, and I want to report to you on a work in progress that is carried out in the NDC. We started with starting with the map of infrasound events reported at the REB and the lab in the last 20 years in Israel region. We see that there are many events. We see that most of the lab events are created using two stations with four information, azimuth and time. I will show it later. And the REB events, with the REB criteria, it's always 3 and above. Those two events we will see immediately, those as calibration events. And I want you, if only to remember what is 500 kilometers on this map. If we will dig a little bit deeper on the events, we can see that on the level of the phases, the time residuals of the phases are pretty good. What you see here, it's the box plot of the lab and the REB. And what I'm reported in numbers are the median. D is how many defining phases, and then how many phases were not defining. And we can see that both in the REB and lab, it's a reasonable time residual. It's a little bit higher in the REB, and which is natural because there are much more information, including seismic station. And the azimuth residual are perfect. We can see that the slowness will not be used at all for location. On the origin level, we can see that the semi-major and semi-minor axes of the aero ellipse are pretty big. In the lab, it's on the order of 1,000 kilometers and 300 kilometers. In the REB, it's a little bit better. It's something like 400 and 200 kilometers. And time residual, the origin time, it's almost approaching 2,400 seconds for the lab and 800 seconds for the REB, which really means, if you remember the scale on the map, that most of the event can be connected to each other and they will be the same. So this is really pose few questions. What is the meaning of reporting on lab events which are based on two stations? Do they really carry any information? How many of those lab and REB events are really real events? We cannot most of the events, we cannot track them back. After the report, if it's not an accident that something happened there, usually you will not find any evidence, and we don't have local networks, so it's a problem. And how we can improve the system. So usually calibration explosions can help us to calibrate the system, and we are very lucky that the GII, together with international calibration, executed two sets of calibration explosion, one in the summer of 2009 with the American, and the second in January 2011 with the CTBTO. Everything was led by Efim Gitterman from the GII. And you can see the difference between the two times, the difference in the pattern of the detection at the different IMS stations. Why it's so important? Because what we learned that Seismic range is performing every year, several times, routine ammunition demolition. It carries it at the same place, at the same location as the calibration explosions. He carries it several times in the winter and the summer, and the yield range from several tons up to 40 tons. It's not optimal because it's not designed as a calibration explosion. What you can see here that the location based on the seismic network, after you perform an hypo DD, double difference methods, really fall on one location, which is almost 1 kilometer from the true location that we know on the calibration explosion. So we have a very good, very accurate location. Moreover, the yield estimation, we are hoping that we can give at least relative yield estimation of those explosions. And the base for that, if you look on those panels, you can see in a last station, the records from several explosions. The two big ones on the upper left are the big explosion, the 80 and 100 ton. And this is one of them, it's a uniform scale. And then you can see the difference between the striking difference between the different yields. If we are taking, the very small is 10 ton. If we are looking on the non-uniform, we can see that this waveform are very similar, which is much more pronounced when you are stacking the event, the seismogram. And then this gives us a hope that we can estimate the yield, at least relative to the big explosions. You can already see a problem that we have, that the range sometimes execute 4 explosions in 1 minute, and then it's starting to be complicated, as we will see later. Another important point is the different times we sample different atmosphere condition, and you can see the striking difference between May and December of 2019, and the difference in the predicted energy arrival to this. In this case, it's I-26 Infrasound station, and apparently it's really important to have it in different times. When we took all the events, the lab and REB event, we tried to match them to those Seismic explosion events, and we took a very loose criteria, but if you remember the medians, so it's not so outrageous. We found 6 REB events and 17 lab events, and you can see that they are matching to 31 local events because, as I said before, some of the events, there are 4 or 3 events on the same time in the Seismic range, and then there was 1 lab or web event corresponding that can match to them. You can see that at the end, although the criteria was 1800 seconds, we didn't reach more than 900, plus minus 900 seconds difference in the origin time. So I will go a little bit deeper with one example. If we look on the May 2019 event, there was reported an event by REB and lab, and there were at Seismic explosion 3 explosions between 1131 and 1133 with yields of 10 and 20, 10 ton, 20 ton, and 22 ton. You can see the Israeli network around the Seismic, and you can see the station, the Infosound station that reported on the event. You can see immediately, this is the seismic waveform from the Israeli network, and you can see the 3 explosions. You can even see some infrasound information on the seismic waveform, and you can see that there is 1, and then there are 2 which are really on top of each other. We did time domain Fisher. We ran the time domain Fisher detector, And here is a broad picture only to show you that sometimes there is an azimuth even before the Fisher ratio values are good. So this is really those two stations. This is I-26, I-33 in Russia, and I-48 in Tunis. You can see that there is something that's coming from this direction, and even here there is something that's coming from this direction. Again, it can be connected to the way that Seismic is performing the explosion. This is our own Infosound, which is collocated with Meron, and you can see that the three explosions. If we look a little bit further, deeper, and we do the zoom, we can see it's really hard to see, but the parameters taken out from the calculation are fitting the expected, the theoretical parameters, and we did the calculation with the time Fisher program from KNMI and with PMCC, which is part of the NDC in the box package. This is a very busy slide, but what I wanted to show here, those are the output of LOCSAT location procedures from the NDC in a box. And what is important to see that actually we cannot decide which of, if it is belonging to one of the three events. So what we see, it's one train that represent those three explosions. You can see that in all cases, the above is the time. The first, this is I-48, so it's time, then slow-net, and then azimuth, and you can see that the residuals of the azimuth are pretty good for the three stations in all cases, which is okay, it's the same location. And the time residuals, you can see that it's getting bigger and bigger, but again, it's reasonable, so it might be that the first arrival belongs to the first explosion. So in summary, we see that the verification regime creates many Infrasound events in the Israeli region. We have explanation for three of them. It's calibration, explosion, and accidents, which are known to everybody. And then it's not straightforward to validate the events because we don't have a local network. What we are happy to see that those low yield events are being detected by IMS station, and it may open us the opportunity to create a calibration set, and we will be giving the location and yield relative to the historical calibration explosion, the relevant AMT, and the list of IMS station. We hope to do for all the events to try to find in Mount Meron Infrasound and the non-Infrasound arrays in order to try to validate them. Thank you very much for listening. Shalom.
Thank you, Yochai. Thank you. It was very interesting and definitely helpful to validate our work. So I think we have time for like 2 questions. If there is anybody in the audience who would like to ask something, I guess Yochai will be happy to answer. In this case, maybe I will have a question. You were showing some shots, one after another in a pretty short time. And we know that at a large distance, this infrasound signal will have quite a long duration. So do you think that we could build, let's say, 3 events, seismoacoustic ones, or how would you suggest to approach a situation like this?
I sincerely don't know. We're only on the starting of the investigation, and this is one of the things that I agree that it's posing a problem because we cannot distinguish between if they are very, very close by. In Mount Meron array infrasound component, we can see the 3 arrivals, the different arrivals. I assume that one of the additional problems, but those are very low yield, so it's not pronounced at the station, the detection. I'm hoping we are in connection with the range, and they are now cooperating with us, and I hope that in the next series we can record nearby observation, and maybe to ask them to delay a little bit the explosion between each other. So we will have not 1 minute, but 10 minutes. But this really, we need to gain the confidence that we are not doing anything harm for them.
Yeah. Thank you very much. So I don't see anything in the chat. So I suggest that we move forward to Sarah's presentation. She is connected to us from New Mexico. She is in Sandia National Laboratory, and her presentation will be on seismoacoustic data fusion. Recorded, yes, it's also pre-recorded, and she will answer.
Hi, and thank you for attending my virtual presentation. My name is Sarah Albert, and I'm a geophysicist at Sandia National Laboratories in Albuquerque, New Mexico, USA. And today I'll be introducing a seismoacoustic catalog and presenting some results from our initial analysis of it. Seismoacoustic fusion is important for gaining a better understanding of any event. However, it's remained largely understudied. And I think Aerosmith et al. Stated it really well in their 2010 paper discussing seismoacoustics. And that is that the solid gas boundary between the lithosphere and the atmosphere has thus acted as an intellectual boundary between seismology and infrasound. So the two have sort of stayed separate as opposed to being fused together to better understand a source. So the aim of this research I'll be discussing today is to really help advance the field of seismoacoustic fusion. And in particular, we'll focus on acoustics in the infrasound band, so less than 20 hertz. Seismoacoustic signals are generated by a variety of sources, including those listed here. And essentially, any event that exerts a force on both the Earth and the atmosphere has the ability to generate seismoacoustic signals. So they don't always produce them all the time because it largely depends on the event size. But these listed on this slide here all have the potential to generate seismoacoustic signals. Seismoacoustic data is generally collected by these methods. The largest is the US Array Transportable Array, or TA stations. These are co-located seismometers and infrasound sensors. However, it's difficult to estimate source back azimuth using a single infrasound sensor. It's really better when we can combine seismic sensors with infrasound arrays. And these two observations can be combined using seismic and infrasound array networks. However, seismic and infrasound stations are usually not co-located. The TA stations are really an anomaly here. So this is a gap that we've noted through this research, and we think that this should really be explored in the future. And that's largely because there's a lack of infrasound array networks. So here on this slide, we have a figure of the University of Utah seismograph network, where there are seismic stations spread throughout the state of Utah. There's also the IMS infrasound network, which is a global infrasound array network that can sometimes be used for seismoacoustic fusion, but the problem is that these stations are pretty far spread apart. So it's unlikely when you're looking at an event that the chances that your infrasound array will fall close to your event are less likely. And then the third figure is a typical US Array TA station, where we've got the seismic sensor buried in a vault and the infrasound sensor above ground. As part of this research, we've generated a state-of-the-art seismoacoustic catalog. And the constraints on the catalog were that the event must have generated both seismic and infrasound arrivals, and the stations must fall within 5 degrees of the source, or about 500 kilometers. The catalog covers 5 countries across the globe, with most of the events occurring in the United States. And here, the figure on the right shows the distribution of these seismoacoustic events. So we can plot the events by source type to see where groups locate. It's perhaps not surprising that the volcanic events locate in Alaska, Hawaii, and Italy, because that's where the volcanoes are located, while the rocket launches locate along the coast. Again, that's where most rockets are launched from. The most common event type in the catalog is explosions. We have 27 of those, and many of these are located at known blast areas, like the Utah Test and Training Range. We were also interested in the number of infrasound versus seismic arrivals for each event type, as this might provide some information about the source. The rocket launch and bolide signals seem to have more infrasound arrivals in general, while the other source types have more seismic arrivals. And this really makes sense because these sources, the rocket launches and the bolides, exert the most of their force on the atmosphere because they're physically traveling through the atmosphere. In these next few slides, we'll look at seismic and infrasound sensors that detected a variety of events. So here, the seismic stations are green and yellow, green being the 3-component and yellow being a single component. And the infrasound arrays are shown by the magenta triangle. So the first example here is an explosion at the Bingham Canyon copper mine near Salt Lake City, Utah. And this event was detected by both single and 3-component seismic sensors, as well as infrasound arrays. And this is because Utah has both an extensive seismic network, as we saw in an earlier slide, but it also has a regional infrasound array network. And looking at these waveforms, we see an impulsive onset at the NOQ infrasound array here. This is just one of the sensors in the array. But the seismic stations also show an impulsive event, but it's of longer duration. So here is a glacier rock avalanche that was recorded in Southeast Alaska. There are quite a few 3-component seismic sensors and infrasound arrays in the area. So this is providing good azimuthal coverage from basically the northwest to the southeast of the source. It's also interesting to note that the waveforms recorded on the seismic and infrasound sensors are fairly similar for this specific event. And we plan on investigating this more. As you can see here, we have an infrasound detection here at N30M and P30M. Both of those are infrasound, whereas the rest of these are seismic, and they have a lot of similarities with the waveform characteristics. This third example shows detections of a SpaceX rocket launch out of Vandenberg Air Force Base in California. There were no infrasound sensors in the area at the time, but the seismic stations did record infrasound arrivals. And the waveforms, if we just look at the seismic waveforms here, they're characteristic of what we'd expect to see from a rocket launch with this sort of delayed onset of the maximum amplitude. So now let's take a deep dive into just one of the events from the catalog. This one is a surface explosion in Utah that occurred at the Utah Test and Training Range on August 1st, 2007. So here I'll take a minute to explain this figure because there's a lot going on here. The way that this figure is laid out, if the triangle is outlined by blue, it means that an infrasound phase was recorded. This orange triangle means that a seismic phase was recorded. And then if we have a combination of the two, that means that both infrasound and seismic phases were recorded at that station. If the triangle is gray, that means there was no detection there. And a big triangle means it's a 3-component seismic station, whereas a small triangle means it's a single component seismic station. So here we're just only looking at seismic stations and the distribution of phases across them. So most of the infrasound arrivals, denoted by that blue triangle outline, are detected to the northwest. We can kind of see that here. This is interesting as we suspected it was an indicator of the predominant wind direction at the time of the event. And it's also important to note that we see a small cluster of infrasound arrivals to the southeast, so right in this area. And this may be a result of possibly the near surface atmospheric conditions, but we really wanted to investigate this more. So we performed ray tracing to get a better understanding as to why those infrasound arrivals were mostly detected to the northwest. And sure enough, the model shows a clear acoustic duct to the west. And this is correlated with the infrasound arrivals and is a good example of where we can use infrasound propagation modeling to better understand the presence or the absence of a signal. The propagation model does not resolve that near surface propagation well, so we don't see that cluster to the southeast. This might just be an issue with the resolution of the atmospheric model that was used in the propagation modeling software. So to summarize what I've shown today, first, we've created a Seismo-acoustic catalog that's robust and state-of-the-art. It has improved geographical and source diversity over others that were previously developed. And we also noted that atmospheric events like bolides and rocket launches are generally associated with more infrasound arrivals. The differences in waveforms between a few of those example events that we looked at show that seismoacoustic waveform characteristics may provide some insight into the source type, because there were some distinct differences in the waveforms based on the source type. And finally, we used an example event to show that infrasound propagation modeling can provide an explanation for directed infrasound arrivals. So we plan to continue this study by publishing a seismoacoustic review paper in the coming months and improving seismoacoustic source location methods as we think these could be very beneficial, and exploring source processes and the advantages of using seismoacoustic monitoring for them. Thank you.
Thank you, Sarah, for this interesting presentation. Again, I think we have time for some questions. So if there are people in the audience who would like to ask something, please, you have your chance now. Ryan Modra congratulated Sarah on her talk. I would like to ask one question then. You were giving an example of volcanoes, and you stated that it's more seen at seismic network than infrasound. We sort of see opposite because maybe we are monitoring it from far. Would you like to comment on this?
Yeah, so for the volcanoes specifically, that's a good question. I think the issue for that, just seeing them more in more seismic arrivals, is probably just due to maybe a lack of infrasound stations. I mean, we definitely have a good amount of infrasound arrays in the Alaska region that do detect volcanic explosions. And you're right, oftentimes when there is a volcanic eruption, it is identified by the infrasound because that eruption is occurring, in the atmosphere and exerting a force on the atmosphere. But in the case of this catalog, at least, we're seeing more seismic arrivals. And like I said, I think that's just a function of the availability of stations in the areas surrounding the volcanoes.
Thank you. And I think I have another question from the audience. I can see the benefit of having similar coverage for seismic and acoustic, but what are the benefits of having them co-located?
Yeah, great question. So yeah, of course, there's always a benefit of having seismic and acoustic analysis, right? For a lot of the reasons that I mentioned in my presentation, but having them co-located is even better because we can get at more information about the source and path effects and things like that. One of the big ones, and something that we actually plan on looking into, is ground coupled airwaves. So where we've got the infrasound arriving and hitting the ground and coupling into the ground, being recorded on seismic. So Kathleen McKee wrote a paper on how to calculate back azimuth with ground coupled airwaves. So in that sense, you would only need one seismometer and one infrasound sensor co-located in order to get a back azimuth. And we have some instances of that in this catalog. So that's one thing that we'll be looking into more to kind of explore that method in different scenarios.
Thank you, Sarah. So I think we can move now to the third presentation, which is given by Ryan Modrak. And this one is on results from a source physics experiment. Ryan Modrak is from Los Alamos National Laboratory in New Mexico, US. It's a pre-recorded presentation.
Good afternoon. My name is Ryan Modrak. I'm a computational geophysicist at Los Alamos National Lab. And in a change from the published agenda, I'll be presenting today instead of my co-author, David Steveman, on the topic of shear waves from underground explosions. And so our results today are based on seismic data from the source physics experiment, phase 1, which consisted of 6 buried chemical explosions in Nevada. All of these explosions, in fact, were detonated within the same borehole. However, depth within the borehole and yield varied significantly. Thus, in analyzing these tests, we used the scale depth of burial concept, which accounts for the opposing effects of depth and yield on surface excitation. And I suspect this may be a familiar term to some. A scale depth of burial is simply the ratio of depth to the cube root of yield. And so if scale depth of burial is low, then an event is said to be underburied. If it's high, an event is said to be overburied. And as it turns out, this experimental approach of varying scale depth of burial while leaving other aspects of the experimental design constant led to some insights about shear wave generation. And so to give one example, here we are looking at some near field time series from accelerometers placed less than 50 meters from the center of the borehole. In just a moment, I'll zoom in on each of these 3 panels to give a better view. But for now, even just at a very quick glance, 2 significant things jump out. The first thing is that moving from underburied at the top to overburied at the bottom, some fairly strong patterns emerge. So varying scale depth of burial, it turns out, causes some quite pronounced changes, even in this very close vicinity to the explosion. The second thing is that both the radial and tangential components of motion were recorded and are being plotted here. And this is significant because we can use this to make inferences about shear wave generation. In other words, by comparing the radial component, which carries compressional waves, with the tangential component, which carries only shear waves, we can make statements about the strength of shear release. And so, zooming in now on the middle of the 3 panels, we get a more detailed view here. This particular panel corresponds to a moderately overburied event. And one thing that jumps out is that the maximum compressional motion on the radial component coincides closely with the onset of shear motion on the tangential component. And so the takeaway here is that there is a strong temporal correlation between compressional and shear wave generation. And overall, there is a fairly large tangential amplitude. There's a fairly large amount of shear wave energy being released. Moving on, these next two panels are for an underburied explosion on the left and a deeply overburied explosion on the right. In both of these two cases, however, there is very little tangential motion actually, much less than in the previous slide. And so this raises the question, what could be happening here to explain this reduced shear release? Well, we have some ideas. What we think actually is that a single mechanism explains most of what we are seeing. What happens is that as the shock wave propagates outward from the wellbore, it induces stress changes on existing joints, causing them to slip in some cases and giving rise to this distinctive pattern in which intermediate events release the most shear energy. And so to understand this pattern, it helps perhaps to think about the joints themselves. So slip only occurs if the joints are locked strongly enough to store significant energy, but not too strongly that the passing shock wave fails to unlock them. And so in terms of scale depth of burial, this translates to low shear release from underburied events because overburden pressure is too low and the joints are not locked strongly enough. On the other hand, it translates to low shear release for overburied events because overburden pressure is too high and the joints are locked too strongly. And so these are the ideas behind the notional scale depth of burial figure on the right. I will be referring back to this notional figure repeatedly throughout the talk. And so as we have seen, support for this notional model from near-field data is fairly strong. To further test the model, we also looked at far-field data. In fact, to this end, we analyzed geophone records from up to 0.5 kilometer away, roughly 30 times further away from the source than the accelerometer records shown previously. In the figure at right, we are plotting a single transverse over vertical ratio for each event. So each of these data points was obtained by averaging over all the available geophones for the given event. And by plotting these ratios versus scale depth of burial, a pattern emerges that matches the notional model described earlier. In particular, we see that at intermediate scale depth of burial, we have the largest shear release, the largest tangential release compared to the vertical compressional release, just as the notional model predicts. Another approach to far field analysis is to actually perform source inversions. In other words, to actually go a step further and to use the observed data along with wave field simulations to try and back out the source parameters. This is exactly what moment tensor analysis attempts to do. Before getting into the details, though, I'll just briefly review that a moment tensor is a weighted sum, simply a weighted sum of force couples. Together, these forces encode the magnitude, the orientation, and other aspects of the seismic source. Now, because there are three spatial directions in which the forces can point, and also three directions in which they can be offset relative to one another, a moment tensor can be represented as a symmetric 3x3 matrix with 6 independent elements. The 6-dimensional space, however, is difficult to visualize, so various lower dimensional visualization devices have been proposed. Perhaps the most natural of these plotting devices is the so-called loon. Mathematically, the location of a moment tensor on the loon is determined by its eigenvalues. If all of the eigenvalues have the same sign, the event is what we call strongly isotropic. It corresponds to low shear release. At the other extreme, if the sum of the eigenvalues is close to 0, the event is strongly deviatoric, corresponding to high shear release. What this actually means in practice is that plotting moment tensors on the loom can help with discrimination. And so to illustrate, all of the seismic events shown in the figure here occurred at or near the DPRK test site. So location, hypocenter location by itself is not sufficient for discrimination. By inverting for moment tensors and plotting on the loon, however, we obtain this very clear separation between explosions, at the top, explosions that produce relatively low shear release, and other seismic events in the middle, which produce much higher shear release. One final methodological question is how we actually obtain these moment tensors. In other words, how we obtain these specific locations on the loon. And we do this by first introducing a misfit function that quantifies the goodness of fit between observed and simulated waveforms. And so in our case, we use a simple L2 misfit function, the one shown here, with a conventional time shift term. Using this function, then, we could minimize, we could apply numerical function minimization algorithms to find a single best fitting moment tensor. Or alternatively, an even more robust approach would be to simply evaluate this function over all the moment tensor space. This is actually what we do. By doing this, we get a globally best fitting moment tensor, as well as a visual sense of how misfit varies. And so when we apply this procedure to the source physics experiment explosions, we get these loon misfit plots in which we again see a pattern involving scale depth of burial. So these plots are actually ordered in terms of increasing scale depth of burial. The main result, looking at these misfit patterns, is that the largest shear release, or in other words, the weakest isotropic character, again corresponds to intermediate scale depth of burial. So the moment tensor results also now are consistent with our proposed shear release mechanism. Now to summarize, we've been talking about shear wave generation from underground explosions. Activation of pre-existing joints is one particular mechanism of shear wave generation, which would give rise to a distinctive behavior with scale depth of burial. Using seismic data from the source physics experiment, we have found patterns consistent with this particular mechanism so far in near field records, far field records, and moment tensor inversions. These results together establish the importance of joint unloading at distances of several kilometers from small chemical explosions, which is significantly further than was previously shown. And finally, I'll just briefly touch on some possible implications. Considering that joint activation effects from small chemical explosions persist to several kilometers, it seems possible that such effects from underground nuclear explosions might persist even further. They might even, in fact, be detectable in explosion monitoring. This is an idea that David Steeman recently put forward. To be clear, we're not arguing that joint activation is a dominant shear wave generation mechanism in explosion monitoring. Instead, I think the question is whether, along with fracture, scattering, and other processes, there might be some meaningful contribution to total shear wave energy from joint activation at monitoring distances. Based on the results shown today, I would argue that this is a question that seems worth studying. Thank you.
Thank you, Ryan. That was a very interesting talk, and we are definitely interested in the results of this source physics experiment. Actually, Ryan is not with us in the room, but he is online, and he will be very happy to answer your questions. I would suggest that maybe you could chat with him on our virtual conference page. I would definitely be interested in whether you plan more of these experiments and when was the last one. I saw some results from 2019. I think this one was just happening when we were having our conference 2 years ago. There was one additional question to Yohai. Julien Vergos asked whether it would be possible to share all event information which occurred these past years, which you were showing us this morning. So you can also contact him online. Or you can answer here.
Yeah, the answer is very simple. Yes, we will be happy to collaborate with anyone that wants. The data is available, both of the Infrasound station in Israel and for the Seismic stations. Yeah, it's supposed to be an open data. This is what we believe in. Thank you.
Thank you very much. So I don't see any other questions or comments, or something has come just now. Okay, Ryan can answer your questions through the chat if you would like to ask him. So do you plan any tests in the future, or was there a test last year? If you can share us with. So the answer is yes, there is a follow-on to the earlier explosions. We can expect more data coming, which are important for discrimination between explosions and earthquakes, and to identify what is the depth of the event. So I think we are basically approaching the end of the session. I would suggest there will be a deeper set of chemical explosions detonated in the Rock Valley area of the Nevada test site. This will be closed at first, but eventually released. Thank you, Ryan. I think we will move to the virtual side of our conference. It will be probably easier. With this, I would like to end this session and encourage you to contact the authors on the virtual side of our conference. There is a chat next to the presentation, and I'm sure they will be happy to see more questions coming from you and share their experience. Thank you very much.